another question. So, a fluid in a closed vessel of fixed volume 0.14 meter cube exerts a pressure of 10 bar at 250 degrees Celsius. If the vessel is cooled so that the pressure falls to 3.5 bar, determine the final temperature, heat transfer, and change in entropy. Yes, this is a full question. It's a very big one, so it's also easy. Just know your formulas, just like we stated our formula before. So the first thing you do, as usual, solution, bring out your parameters. Parameter given. Okay, parameters given. So what are the parameters here? Remember, closed vessel. The vessel is closed. That means has a fixed volume. Fixed volume means V1 is equal to V2. The volume doesn't change, so it's constant. So that makes it a constant volume process. Okay, so which is 0.14 meter cube. Or better still, I would prefer to write it this way. Okay. This is equal 0.14 meter cube. So the pressure P1 is 10 bar, T1 is 250 degrees C. Okay, yes. Now P2 is equal to 3.5 bar, and then we are asked to find T2, Q, and change in entropy. Okay, so but a fluid can be a vapor, can be a liquid, it can be a gas. Okay, so we are going to make two assumptions here. We're going to assume it as a vapor and as a perfect gas. So assuming that the fluid is a perfect gas or an ideal gas, so assuming the fluid was an ideal gas. Okay, assuming this fluid was an ideal gas, so we use our ideal gas equation at constant volume, which is P1 over T1, which is equal to P2 over T2. Okay, now therefore T2 will be equal to P2 times T1 all over P1. Now we know that our T1 is equal to 250 plus 273. That is what? 523 Kelvin. We convert it to Kelvin. Alright. Now that means T2 will be equal to 3.5 bar times, of course the bar will cancel out, so there's no need writing the bar. So we have 523 Kelvin over 10. So what will this give us? It will give us that T2 is equal to 183.05 Kelvin. So let's mark it this way. because we'll refer back to it. Okay. Yes. Now we said you should find the heat. You should also find the what? Heat transfer. So what is the heat transfer? How do we get it? So the first law, from the first law, we have that Q plus W is equal to U2 minus U1. Okay? Yes, alright. So we all know that W is equal to what? P dW is equal to P dV. So that W is P V1 minus, or we can say V2 minus V1, which is still 0 because it's at constant volume. So that leaves us with Q is equal to U2 minus U1, which is equal to mCV T2 minus T1. Okay, since we've written M but we don't know it, so we have all the parameters to get it. So Q remains mCV T2 minus T1. So but PV is equal to mRT. Okay, the value of R is 0.287 kilojoule per kilogram Kelvin. So how do we get our mass? We have volume. Okay, have our volume. I hope it was written in the parameters. Yes, it was written in the parameters. So the mass of course is equal to PV P1 V1 over RT1. So that will give us 10 times, converting bar to kilo is by dividing by divide it by 1000. So whatever is remaining is 100. So we have 10 raised to power, or let's write everything. 1 bar, okay, I'm coming, times 0.14 over 0.287 times 10 raised by 3, because it's kilo. See the kilo here. We are writing everything in standard units so that we will not get confused. So 1 bar is equal to 10 raised to power 5 Pascal. Okay, so that is why the bar became this. So this standard unit. You can see also 1 bar is 10 raised to power 5 what Newton per meter square. Alright, then finally, doing the necessary calculation, we have that M is equal to 0.9327 kilogram. So with that, we can find our heat. So since it's a perfect gas, okay, since it's a perfect gas, Q is equal to what? mCV T2 minus T1. But CV is what? Specific heat capacity at constant volume, and the value is 0.718 kilojoule per kilogram Kelvin. So we have our, what was our T2? Let's go up. Our check. 183. T2 was 183. 183.05. Okay, 183.05 minus T1, that is 523. Okay, now finally our heat will be minus 227.66 kilojoule. So the minus sign shows that heat, the negative sign shows heat rejection or rejected heat. Okay, so this is II. So II is the entropy change. Alright, yes, entropy change, which is S2 minus S1. The formula is CV ln T2 over T1. Okay, you know what CV is? We have all our temperatures, so we can just impute them by saying this ln T2, which is 183.05 all over 523. Okay, that will be finally S2 minus S1 will give us, what will it give us? Minus 0.754 kilojoule per kilogram Kelvin. That's what it will give us. So for a unit mass, for a mass, change in S equal to ms2 minus s1, which will be the mass we got, which is 0.9327 times minus 0.754. So change in entropy will be minus 0.7035 kilojoule per Kelvin. Okay, as you can see, we've solved this, but under the assumption that the fluid was an ideal gas. So we are going to assume the fluid also was a vapor. Okay, assuming the fluid was a vapor, we are going to also solve with that assumption. So now, assuming the fluid to be a vapor, assuming the fluid, was a vapor or steam. So assuming it was vapor or steam, so our V1, which is this meter cube, our P1 is 10 bar at T1, which is 250 degrees C. So now, from the saturated vapor table, you go to the saturated vapor table in your steam table, you go to P equal to 10 bar at P equal to 10 bar, P1 equal to 10 bar. You notice that The temperature at pressure 10 bar is lower than 250. So temperature Ts, saturated temperature, is 179.9 degrees C. So this temperature is lower than T1, which is equal to 250 degrees C. Hence, is a saturated steam. Hence is a superheated steam, since the temperature given is greater than the saturated temperature. So hence the steam is superheated. The steam is superheated. So you go to your superheated table. So from the superheated steam table, at P equal 10 bar and T equal 250 degrees C, we have that specific volume. Okay, we have that specific volume is equal to 0.2328 meter cube per kilogram. We also have our internal energy, 2711 kilojoules per kilogram. We also have our specific entropy at 6.926 kilojoule per kilogram. Right? Yes. So now these are the conditions at the inlet. Okay, at state 1, these are all the conditions. So we have gotten the specific volume, but remember that specific volume, like we did before, is equal to what? Volume over mass. So remember that our volume, which is V1, which is still the same thing as V2, is 0.14 meter cube. Okay, now you go ahead and look at what you have. So specific volume now, of rather, can I say, the mass M will now be equal to mass M will now be equal to volume over specific volume. Which is big V over the small one. So the specific volume was, the big volume was 0.14, the specific was 0.2328. Dividing, we have the mass to be 0.60137 kilogram. So this is the mass. Okay, so but still the specific volume at the first state is equal to that at the second state, which is still 0.2328 meter cube per kilogram. So remember, back to the question. They gave us the second pressure, that is P2. They said P2 is equal to 3.5 bar, and we have that V2, that is specific volume 2, is 0.2328 meter cube per kilogram. So you go to the saturated vapor table. From the table, saturated table at P2 equal to 3.5 bar, we have that Vg is equal to 0.5241 meter cube per kilogram. We also have that UF is equal to 584 kilojoules per kilogram. Then we have UG is equal to 2549 kilojoules per kilogram. Then SF will be 1.727 kilojoules per kilogram Kelvin. So these are the values. Okay, we have SFG, which is 5.214 kilojoule per kilogram. So these are the values from the saturated table at pressure 3.5 bar. If you check there, you will see all these values. So remember, the specific volume is equal to this XVG. So at the second state now, we are finding the dryness fraction. Okay, so dryness fraction will be 0.2328 over the Vg, which is this. So dryness fraction is 0.44. Of course, it's less than 1. So the states at the second state is a wet. It's under a wet condition. So we're going to move to the next page. This page is finished. We have reached the end of the page. So move to the next page. Okay, so U2 is equal to what? UF plus X UG minus UF. We stated this formula, recall from the last episode recall from the last tutorial video we mentioned all these formulas. So recalling from that, we decided to write it down. So U2 is equal to, we got the value of UF was 85584 plus 0.444. UG is 2549 minus 584. So doing this, we have that our U2 will be 1456.5 kilojoule per kilogram. So that's it. Now for the entropy, also know that entropy is equal to SF plus XSFG. Of course, 2. So S2 is equal to SF. We found that SF to be 1.727 plus 0.44 into SFG, which is 5.214. So doing this, we have that our entropy is 4.042 kilojoules per kilogram Kelvin. So finally we can answer the questions. The questions were: 1. The final temperature. So the final temperature T2 is the temperature at P2, which is what? Our P2 was, what was our P2? 3.5 bar. So the temperature at 3.5 bar from the saturated vapor table is there. After pressure, the next thing you look at is temperature. So just get the value from there. The saturated vapor table is T2 is equal to 138.9 degrees C. So that is the final temperature. So the next thing is the heat. Remember that Q plus W is equal to U2 minus U1. So but there's a mass, so we can write that Q plus W is equal to M U2 minus U1. So but for a constant volume process, W is equal to 0. So heat is M U2 minus U1. So Q will be what? 0.60137. That is the mass we got. So then U2 1456.5 minus 2711. All these values are in the previous page. Okay, they are all in the previous page. We just solve them. So solving this, you have that your heat finally is 754 as minus 754.45 kilojoules per kilogram. So the minus sign, so this is what is the heat rejected due to what? Negative. Okay, so the entropy change here now, the entropy change, which is S2 minus S1, is, we have your S2, we got S2 as this, and S1 is in the other page too. So finally when you subtract the two of them, you have this as your final answer. You have this as your final answer. So we solved it both as a steam and as a perfect gas. So this is it. We have come to the end of this episode. So stay tuned for more tutorial videos. I will be treating, in the next video, be treating the constant pressure process, which is the isobaric process. So stay tuned.
It leads to liquor on some ladies. Yeah, we did turn up on a daily. It's how I walk up. Yeah, soft walk.